Hello everyone, I'm Yaqian from Beijing Institute of Technology, China. I'm honored to present the paper, IriTrack Face Presentation Attack Detection using iris tracking. This is the joint work with my teachers and teammates at BIT. Nowadays, face recognition systems have become popular as a reliable and convenient way of user identification, access control, and online banking payment. A face recognition system is composed of presentation attack detection and face recognition. The former ensures that the image or video samples are provided by a genuine user, while the latter has to determine whether the user is authorized. In this paper, we focus on developing efficient PD methods. In presentation attacks, an adversary attempts to subvert a recognition system by presenting an artifact that mimics facial biometric features. In order to detect artifacts, PID methods are proposed. PD methods can be classified into two categories. Methods using static features are computationally expensive and responsive, but error-prone and unstable. Methods using dynamic features can better defend against artifacts, but increase storage and computational overhead. In this paper, we pay attention to the PD methods relying on eye motion detection or eye-based challenge response detection. SIGCHI proposed a method based on human pupil dynamics. That is, irises will change their sizes in different light intensity levels. However, pupil size can be altered in different psychological states, leading to degradation of detection accuracy. Ali et al. Proposed a method based on an assumption. The horizontal or vertical movement of real eyes is more stable than that of unreal eyes. However, the gaze of a real person changes unconsciously, which results in an offset of gaze positions. The goal of this paper is to achieve an efficient and robust PD method via tracking the position of human irises. There are mainly two challenges. On the one hand, how can we decrease the influence of noises and different adjustment strategies? On the other hand, we should make sure the method is efficient and robust. The main contributions are as follows. First, we propose IriTrack, a PD method that leverages polyline-based iris tracking with computational simplicity and no special hardware. Second, we designed two key components of IriTrack, namely a probability-based PD pattern generation method and a precise iris tracking method. Third, we conduct extensive experiments to demonstrate the effectiveness and efficiency. The idea is inspired by the screen lock pattern systems, where lines are drawn by fingertip over dots and then compared with the pattern predefined. In IriTrack, a user is required to move eyes along a pattern, where the iris trajectories recorded are compared with the pattern to draw a conclusion. The workflow is described as follows. First, the system randomly generates and displays a PAT pattern on the screen. So the user is required to follow the pattern with eyes, and the trajectories of irises can be recorded by a camera. Finally, the collected trajectories and the given pattern are fed to the Similarity Measurement module to draw a conclusion. To achieve a balance between time efficiency, security, and accuracy, we design a probability-based model of pattern generation. Specifically, we generate a pattern with only one line segment and then judge whether a new dot should be added. If the result is positive, we select an angle and a line to update the pattern. Finally, we compute the goodness of the generated pattern to ensure the time efficiency and security. To track iris movements, the tracking module utilizes the camera to acquire images at a fixed frequency. Then it employs the Dogman's integral differential operator to detect the center of irises. In terms of similarity measurement, to eliminate the influence of unconscious eye movements, we view the angles as the skeleton of a pattern. Specifically, we compute iris positions first and recover the angles. Then we measure the similarity between the skeleton and the pattern. The system was deployed on commercial PC and experiments were conducted with the default setting. We select three comparison methods and use ABCR and BBCR as accuracy metrics. First, we investigate how time, cost, and accuracy vary according to different values of parameters. In the experiment, the generated patterns are simplified into a polyline consisting of only 3 dots. For one pattern, 4 participants are involved and each completes 10 times. The results show that shorter lines with a higher speed are preferred to improve time efficiency. To balance time efficiency and accuracy, we select the values of speed and line segments. Then we evaluate the performance of IriTrack and other PD methods. The results show that IriTrack always owns the highest detection accuracy with moderate time and memory costs, which shows that IriTrack has the best performance. We also evaluate the effect of environmental and positional factors on performance. For the factor of light intensity, we find that the detection accuracy maintains at a high level as the light intensity changes. For the factor of distance, we find that IriTrack achieves stable detection accuracy, and for the factor of height pose, we find that an irregular facial pose can identify more artifacts. Finally, we select 5 different combinations of the 3 factors. The results show that combining these factors will not lead to addictive effects on performance, and the accuracy is determined by a single dominating factor. The experimental results show that IriTrack is robust to changes of lighting conditions, face, camera distances, and height poses. Now I'd like to conclude this paper. We propose an efficient and robust PD method suitable for deployment on resources-constrained devices while tracking the position of human irises, and demonstrate its effectiveness and efficiency. In the future, we will further investigate more practical influence factors to improve the performance.